Hello to everyone. Welcome back to my YouTube channel, Jeet Academy. In this particular video, I'll be discussing about a very important topic in algebra that is called as logarithms. It's an important tool and this will help us in, all the different topics as well. So if you belong to IB, if you belong to Edexcel, O levels or IGCSE or CIE, this video is for you. Now let's quickly start. Now, what exactly is this logarithm? So basically, this tool was invented by John Napier. Okay, so he was a mathematician who invented this, and the reason he invented this is, let me take an example. Let's suppose if I give you a weird multiplication like this, 3.18 to some power as 2.17 multiplied by 4.22 to the power of 9.21, whole thing divided by 7.23 to the power of 8.92, something like this, right? So what happens over here is this calculation, if I ask you to do this manually, right? So this is enough to leave maths, isn't it? Yeah. So John Napier, what he did is he invented a tool called as logarithm, which will convert this entire product, which looks weird, to simple basis. Okay, so that it becomes simple because it was invented back then in 17th century and there were no calculators and all. Right, so it was a very tedious process to do these kind of multiplications, right? And therefore the reason goes for slow advancement in the astronomical data as well. Right, whatever research used to happen, the rate at which it used to happen used to delay because of these complex calculations and all. Right. So let's understand what John Napier has given us. So basically, John Napier says for every positive real number, right? For every positive real number, and we know that real number is root 2, root 3, all the rational numbers, all the whole numbers, all the fractions, integers. Okay. So it can be written in an exponential form. Okay. For every positive real number, it can be written in an exponential form, which is basically a form called as, you know, n equal to a to the power x. Okay, so n is my number, which is a positive number. A over here is called as the base, and x over here is called as the exponent. All right. So any number. So let me take few examples over here, then it will be more clear. Let's suppose if I have 8, right? So I could write 8 as 2 to the power 3. Getting it? Similarly, I can write this 8 to different base, which is 4, as, so how I can write 8 in terms of 4? So I have to square root of it, right? So that it becomes 2 and then cube it, isn't it? So 4 to 3 by 2 power, that means 4 raised to 3 halves will eventually give me 8. Okay. Now, if I ask you, can I write 8 as a base of 1? To 1 to any power will always be 1, isn't it? Now here it fails. So this is not possible. Got it? So basically, I cannot write any number, right, except 1 to the base 1. Are you getting this? So basically, we'll come to this. Now let's understand the process, what he exactly did. So far what we have seen, if I have any positive number n, right, any positive number, it can be written as a positive base to positive power. Okay. So for example, we had already seen that 8 is equal to 2 to the power 3, isn't it? Now, how John Napier writes this, let's understand this John Napier way of writing this number in a log form. Okay, what is this logarithmic? So writing this exponential form similar to log form. Okay, so how he writes? He writes log of the number to the base a is equal to x. Getting it? Where the number n is positive, the base is also positive, and it is not equal to 1 because 1 to any power, right, will remain as 1 itself. Are you getting this? So these are the three conditions which applies over here. Okay, so how he writes the same exponential in terms of log is log n to the base a, which is equal to x. So another way to read this is what power of base a is this number n, and which eventually turns out to be x. Okay, so another way to think of it is when I remove this log this function, so I write a is a base over here. So when it goes to right hand side, it will still remain a, and therefore I can write like this. Okay, so this exponential notation and this logarithmic notation is the same thing. Okay, so let's understand some examples. Let's suppose we are given with log of 32 to the base 2. Okay, so try this out. How do I read this? What power of 2 will eventually give you 32? So that's 5, right? So 2 to the 5 power. So if you feel this is difficult, then you could assume, let's suppose you don't know what answer is it. So assume it to be x. So simply if I write it as exponential form, I could write it as 2 to the power x. Now 32 is basically 2 power 5. So 2 power x. And therefore on comparing the powers, we therefore get x is equal to 5. Are you getting this thing? Similarly, so this is first example. Let me take the next example. Let's suppose we have log of 16 to the base 1 half. Okay, so let's assume that this value is x, and therefore I can write 16 as equal to 1 half to the power x. Now 16 is 2 to the power 4. 1 half is 2 to the negative 1, whole thing to the power x. And therefore, what we can write here is 2 to the power 4. From elementary classes, we know that power to the power gets multiplied, which turns out to be 2 power negative x. Now both the side bases are same. Therefore, comparing the powers, we get x equal to negative 4. Does that make sense? Right? So this is how we convert basically. Okay, writing one number to different ways. That is what basically this log tells us, and it helps us. Okay, now let's understand the constraint where it is possible and where it is not possible. The reason I have written here in the first place, that it is valid in a positive numbers, right? So let's check that. So we have discussed over here with positive numbers, right? For every positive real number. Now let's talk about the negative real numbers. Let's check that. Suppose, let's take it as this. I have log of 8 to negative 2 base. So do we have any solution here? Negative 2 to any power will give you 8? No, right? So that's not possible. But then you will say, so if I take it as negative 8 to the base negative 2. All right. So here it is defined. So the answer is 3. Negative 2 to the power 3 is basically negative 8, isn't it? Negative 2 to the power 3 is what? That's negative 8. So here it is valid. Okay, but then how long you will be checking like this that it is valid for this particular number, this negative number, isn't it? So it will be very challenging and tedious process. So what John Napier did was he removed all these constraints and he says log is valid only for positive real numbers. Okay, even though sometimes it is valid here in negative numbers. So we remove these constraints and it should be valid for all the real numbers. And therefore, I can conclude when I write log of n to the base a equal to some number x. So my constraints are n should be greater than 0. That means it should be non-negative. Okay, a should be greater than 0 and it should not be equal to 1 for the very reason that 1 to any power is 1 itself. Okay, so these are the three conditions I have to keep in mind. Does that make sense? Now let's try to do some questions based on this, what we have learned. Let me give you the first question here. Let's suppose you have log of 1.3 bar to the base of 4/3, right? So you need to figure out this one. Now pause this and give it a try. Now let me show you how to do this. Basically, this notation you have already learned in IGCSE and MYP. if you are in IB curriculum right now. So 1.33, this 3 bar stands for 333, and it keeps on repeating itself. All right. So 4 over 3. So you assume this to be x. How do you convert this repetition of decimal to a normal fraction? So this decimal is after one point, right? So one digit. So we multiply both the side by x, and therefore this becomes 13.333. So I could write this thing as 12 plus x, and this becomes this. Now subtracting x both sides equal to 12, and 9x is equal to 12, and therefore x is equal to 12 over 9, which is same as if I cancel this out by 3, 3 times 4 and 3 times 3. Okay, 13.333 can be written as 12 plus x, where x is 1.333. I hope you understand that step. Okay, so basically this base and this is same, right? So what will be my final answer? Shouldn't it be 1? Because what power of 4 by 3 is this? So basically this question turns out to be 4/3, and the base is also 4/3, right? So this is equal to 1. So very important result we have seen over here. When the base and the number are same, we get it as 1. Okay, very, very important. And then similarly, I could also check for, reciprocal. Let's understand this. Let's suppose we have log of 2 plus root 3, and the base over here is 2 minus root 3. Okay, so now check the product of these two. So if I multiply 2 plus root 3 with 2 minus root 3, so we basically get 4 negative 2 root 3. So this is, multiplication a plus b times a minus b, which is same as a square minus b square. You could apply the direct identity over here. So 4 minus 3, which is equal to 1. And here, if you just simplify this, you will get positive 2 root 3 minus 3. So these two cancels out. 4 minus 3 is 1. Okay. So whenever the product of the base and the number is 1, okay, whenever the product of the base and the number, so remember this important result, whenever base multiplied by the number is equal to 1, that means they're reciprocal of each other. Okay, these are reciprocal of each other. Getting it? So you can try this, the rationalizing of denominator 1 over 2 plus root 3. If you rationalize this, you'll basically get 2 minus root 3. Okay, so the answer of this will always be negative 1. Okay, because this is the reciprocal of this. So what power of 2 minus root 3? The power of this would be negative 1, so that it becomes 1 over 2 minus root 3. Does that make sense? Okay, now let's understand the different cases here. Okay, so let's suppose, important note, let's take as 1 to the base 2. Okay, so what power of 2 will give us 1? Answer is 0. 2 to the power 0 is 1. If I have log 1 to base 100, 100 power 0 is 1, so answer is 0, isn't it? Then I have base 2, let's say 102. Then what will be the answer? What power of 102 will give you 1? So it is 0, right? And therefore from here, I can conclude that log 1 to any base, right, will always be equal to 0. This is also an important result. Okay, so far we have seen that the number should always be greater than 0. The base should always be greater than 0. Log 1 to base, any base is 0. And we have seen if any number and the base multiplied together gives you 1, that means they are reciprocal of each other, and the answer will always be minus 1. Okay, and when the bases and the number are same, we get eventually 1. All right. So I hope you understood the basics of log, how it converts. Basically, let me give you an intuition of why exactly it is needed, right? So you could have thought of this scenario. For example, let's suppose if I ask you 2 to the power x is equal to 32. So what's x, right? So you could write 32, this number, particular number 32, as a base of 2. I can write it as 2 power 5, and therefore x becomes 5, right? But the same question, if I put it as 2 to the power x is equal to 33, right? Now I cannot write 33 in terms of base of 2. Are you getting this? Right? So then how do I find this x? So what we do is we take log both sides like this to some defined base, let's say 2 itself. Okay. And then using the laws of, log, we find the value of x. So we'll do this in the next video. Okay. So stay tuned. If you like the content, do subscribe my channel, share it with your friends, and I'll be discussing all the concepts in this channel. Okay. So bye bye. Take care.